Hello, my name is Brian Dyck. I'm a software engineer, and this is my YouTube series on the HackerRank interview preparation kit. Currently, we are going over the array problems, and this problem in particular is the minimum swaps 2 problem. This is the second problem that we've seen that is of medium difficulty, so let's get to it. You're given an unordered array consisting of consecutive integers 1, 2, 3 to n. Without any duplicates, you are allowed to swap any 2 elements. You need to find the minimum number of swaps required to sort the array in ascending order. For example, given the array R is equal to 7, 1, 3, 2, 4, 5, 6, we perform the following steps. And then it goes on to list all of the steps, step by step, and how the array looks at each intermediate step here. I'm not going to go over this because I think it's more confusing than the actual solution. So I'm just going to skip over this. If you want to pause the video and look at that carefully, go for it. But I think it's more confusing than just going over the solution. And in their particular example, it takes 5 steps to sort the array. So let's go to the function description. Complete the function minimum swaps in the editor below. It must return an integer representing the minimum number of swaps to sort the array. Minimum swaps has the following parameters: R, an unsorted array of integers. So, in other words, we're given an array of integers, and then we need to return the minimum, and I think that's a key word here, minimum number of swaps to sort the array. And I think this scares a lot of people away from this problem, and I think that's why there's a 30% fail rate, is because people are scared of the minimum. I think it's that, and I'm going to explain it in a second. I think the explanation is really, really bad here. So they give us their sample input and sample output. So they give us this array and say the sample output is 3, and then let's go to the explanation. Now I'm going to go over this. I'm going to explain why this is confusing. So we're given this array, 4, 3, 1, 2, and then we swap 0 and 2. So we're going to swap this 4 and put it here, and then we put the 1 here. That seems like an optimal move, right? Because we're getting our 1 in the right position. So maybe at this stage you might be thinking, well, they're just going to look for whatever belongs in this position, and then they are going to swap out this one there, go into the next index, find the 2, put the 2 there. No. But no, that's not what they do. That would be logical, but that's not what they do. So the next step, they go ahead and swap the 1 and 2. So that 4 that they just moved here to the 3's place, they're going to swap it with the 3. Then the 3 that was there, they're going to move it to where the 4 is. Interesting choice, but okay, whatever. Then we are going to take 1 and 2, or after that, we're going to swap 1 and 3. So we're going to take that 4, and we're going to swap it with the 2, and this makes sense. Now the question is, how did this medium step, this middle step happen? This middle step makes no sense to me on any way that you could do this algorithmically. If somebody has this algorithm, please tell me about it, because this sounds brilliant. But it also seems very confusing. I don't understand exactly what's happening here. And I think this is why a lot of people get tripped up on this, because this example is so overly complicated on something that is very simple that it makes this problem harder than it needs to be. So without looking at the solution, I'm going to explain how we can get 3 swaps done in this to get the right solution. So my algorithm, what I'm going to do is I'm going to just look at the first number. I'm going to move this first number to where it needs to go. So we're going to take this array. Let's see if I can pull up a notepad. Yeah, I can. Nice. Boom. Okay. So we've got 2, 3, 4, 1, and 5. So this is our current array. Can I make this bigger? Let's see here. Zoom. Control plus. Okay, cool. Way bigger. Okay, that's as big as it goes. So I have 2, 3, 4, 1, and 5. So let's say for my first step, I'm on the 2. I see it's a 2. I'm going to swap it with whatever is in its place. So this is the 2's place. I have a 2. So I'm going to go and say this is now 3, 2, and then 4, 1, 5. That all stays the same. That means we have one swap. All right. So now I have a 3 here. I go to whatever's in the 3's place. 3 is a 4. I'm going to swap these two. So I have 4, comma, 2, comma, 3, comma, 1, comma, 5. And that is 2 swap. All right, so now I have a 4. I'm going to swap it with whatever's in the 4's place. And then I have 1, 2, 3, 4, and 5. 3 swaps. And I'm done. So notice something that is different. There's something that is the same between my solution and their solution. But let's look at their solution. So their solution, let me just kind of move this like that. So their solution here, their explanation, they're going to move 2 and 3. So they're going to take what's the position that is here and swap it with 3. Then they are going to take 1 and 2 and swap 1 and 2. And then they're going to do 0 and 3. And then they're sorted. So they do it in the same number of steps. So there's something similar here. The similar thing is if they do it in the same number of steps, what is not similar is theirs doesn't seem to make sense on how they're doing this algorithmically. So my algorithm is very simple. I look at the number in the current index. I see if the current index is equal to what it's supposed to be. If it is not, then I swap it with where it belongs. And then whatever was where it belonged would have had to have been the wrong value. So then I have another value that would have had to be swapped either way. Then this value gets swapped with whatever was there. Now I have something that belongs in the 1's place. So I can move on to 2. 2 is in the right place, so I can move on to 3. 3 is in the right place, I can move on to 4. 4 is in the right place, I can move on to 5. 5 is in the right place, I'm done. Takes 3 swaps, but this is something that you can explain and think through algorithmically, and it is very simple. And some people might be like, oh yeah, but how do you know that's the minimum number of swaps? Well, let me explain. So since 2 is in the wrong spot, whatever is in the 2's place is not 2. So it's going to also need to be moved regardless. So no matter what, this value is eventually going to have to be moved. We're just doing this as a swap to put this in the right place. Whenever we're doing this, we're going to get, at worst, if every number is in the wrong position to begin with, we're going to have n-1 steps. That means that this solution should work in almost, or this will always work out to be the minimum number of steps. And if you want it more rigorously proved, I could leave you a long form proof somewhere. I don't know, maybe I'll attach it to a Google Doc or something and upload it. I'll probably want a pen and paper to do actual math because I hate using, what's the program called? It's not Laplace, but it's something mathy. It's basically like programming for math papers. Anyway, let's get back to the coding. But it does work out to be the minimum number of swaps if we simply put whatever is at the index we're looking at into the right place. So let's go ahead and code that algorithm that I described. So we have int num swaps. This is going to start out to 0, obviously, because we haven't swapped anything yet. And then we're going to say for int index is equal to 0. And as long as index is less than the array dot size, we are still in bounds. And we're going to increment the index. So there's our for loop. Now within this for loop, we're going to nest a while loop. So this while loop's condition is going to say while index plus 1 is not equal to array sub index. We're going to keep doing this. So the reason why this is our condition is we are going to look. So it's plus 1 because instead of 0-based numbers, we have 1-based. So we go 1 to n. And our array's indices are going to be 0-based. So in other words, the index of the array plus 1 is equal to what's actually supposed to be at that index. Okay, so that makes sense there. The reason why we're doing this while loop is we are going to be swapping this value with whatever we find at its place, and then we're going to keep doing that until the index at this place is the right value. Whenever this for loop terminates, then we have the array sorted out. So let's go ahead and let's mark down some values. So we're going to say int swap index. So the index we're supposed to swap with, the swap index, is going to be equal to the value at array subindex minus 1. And this is for the same reason we do plus 1 on the index when comparing its value. The value minus 1 is equal to the indices that this belongs at. Then we also want to have the values for both. So val at index is going to equal array subindex. And you can obviously do this in fewer steps, but I just want this to be as clearly written as possible, so you can just look back at this in English and know exactly what's happening here. Val at swap index is equal to array sub swap index. Oops. All right, so then we're going to simply take the array at index and set its value equal to val at swap index. And then we're going to take, array. And then we're going to take the array at the swap index and set its value to val at index, like so. And then after doing those steps, we've performed a swap. So we need to make sure we increment the num swaps. And this continues, this while loop continues until this is equal to the value at index. That should be there. The value of index is equal to the value at index. And then we keep going through this for loop until all the indexes are equal to their position. At the end, we have the total number of swaps. And I explained before that this is going to be the minimum number required to get it into the right position. So return num swaps. And now let's run our code to see if this works. Bam. So there we go. We passed all the sample cases. And now let's test our efficiency levels. Oh, by the way, something that you'll find interesting is at worst case, if the very last swap sorts the array, our while loop at most is going to run n times. The for loop at most will run n times. So that is, and by the time this is run, so when I say at worst on this while loop, it's not on each iteration. If this ran n times at any point, then our array is fully sorted. So this, over the lifespan of this for loop, will only run n times. And this for loop runs n times. So that would be n plus n, not n times n, like most nested loops, because of the nature of the problem. So this solution is only n space complexity, and it is only 2n time complexity, which is still an order of n. So this is an n solution to the problem. Just thought I'd throw that out there. Okay, so let's go ahead and submit code. And there we go. We have solved this problem. So if this video was helpful to you and you're struggling with the minimum swaps to problem and this helped you get through it and understand the problem a little bit better, please leave a thumbs up on this video and subscribe to the channel for more HackerRank problem solutions. Also, please, if you have any questions, if you're not satisfied with my explanation for why this works, leave your further questions in the comments section below, and I'll do my best to get back to you and answer those as soon as possible. If you want to see more of this content, make sure you subscribe. See you later.